Yep. So last time that we discussed the Lasso and rich regression. So remember that we are estimating basically the same model as the traditional linear model. So it does not have to be linear model, but as an easiest example that we choose the linear model. So the problem is that when we have a large number of candidates of predictors, x1 to xp, what's the best way to choose the best set of predictors, or what's the best way to estimate the beta naught to beta p? And we discussed three methods. The first, we discussed the subset selection. So we just choose the subset of p predictors. We say maybe we only choose the d predictors out of p. Then the model only keep useful predictors. So prediction performance can be better. And then we discussed the shrinkage method. So they use all p predictors, but they make the coefficients smaller. So we discussed two methods. The one is the rich regression. The rich regression makes these coefficients smaller than usual the least square estimates of parameters. So often least square estimates they have the large parameters in absolute values because of the multi-collinearity. So suppose that x1 plus x2 is equal to negative x3. So we have the three predictors, but we have some linear relationship, or maybe almost linear relationship in reality. Then, for example, this model, y is equal to x1 plus x2 plus epsilon, and this model, y is 2x1 plus 2x2 plus x3 plus epsilon. So these two models almost give the same fitted value, because x1 plus x2 plus x3 is 0. So you can see if we add x1 plus x2 plus x3, then this model becomes this model. So that means even though fitted value are similar for these two models, possibly some models have the large coefficients, the 2, 2, 1, sometimes maybe 100 times x1 plus 100 times x2 plus 99 times x3. The still fitted values are similar to this simpler model, y is equal to x1 plus x2 plus epsilon. But that is sometimes a problem, especially the x1 to xp have some measurement error. Measurement error will be exaggerated if coefficients are larger. So we have some motivation to make the coefficients smaller. And the rich regression is used for that. And the rich regression, the estimation method is slightly different. What's the difference between rich regression and linear ordinary least square estimate? That is this term. So ordinary least square minimize the residual sum of squares, but the rich regression have additional term, lambda times beta square. So the lambda is a constant, given constant. And so the large coefficient is penalized. So we have to make RSS smaller, but at the same time, we have to make the size of coefficients smaller. So it balances between those two quantities. And we also studied another method, the Lasso. Lasso is very similar to rich regression, but this penalty term is the lambda times summation of absolute value of beta j. So these two functions are behave different. I would say the f of x, the function f of x is equal to x squared, and the function maybe g of x, which is the absolute value of x. So these functions behave differently because for small x, maybe it's better to put beta, maybe I would say some beta square and beta absolute value. So these two functions behave differently. So if beta is very large, beta is very large, the penalty is very large for this f. The value is very large for f. F of beta is this shape. So this is y is equal to f of beta. And the g of beta is this. So the penalty isn't really large when beta is very large, but the beta is small, the penalty is much larger than f. So that means that for this lasso regression, if beta is estimated beta is small, then the lasso makes that to 0, that shrinks it to 0. Because the small difference in parameter doesn't change fitted value much, but the penalty gets much smaller if we use g. So that means that if estimate, for example, the beta is equal to such as the 4.4, yeah, so if beta is equal to 4.4, that may become 4.3, but if beta is equal to 0.1, then the lasso regression, it makes it 0. So that is typical case. Rich regression, the squared penalty on the size of beta. So if beta is 4.4, that may makes it 4.0 because the 4.4 square is much larger than 4.0 square. So even if estimate will be changed, still the rich regression have, the kind of larger motivation, more motivation to make beta smaller. But beta is small. Basically, the rich regression almost does not penalize it. 0.1 square is a very small number, so probably it doesn't change much, maybe 0.09 or something. Sorry, the lasso, it makes it 0, but the rich regression, it makes it slightly smaller. So in rich regression, there's still the most parameters, estimated parameters becomes non-zero, but the lasso, many parameter becomes 0. So that's the difference. And we discussed the difference between lasso and rich regression and the some mathematical the equivalency. Yeah, so then we compare the lasso and rich regression a little more. So lasso tends to give a simpler model since more parameter estimates becomes 0. So in general, we cannot say whether lasso or rich regression is better. And lasso works better if the true model has few non-zero parameters. Yeah, for example, in some applications, maybe you have the 1,000 candidates of predictors, but you know that only the 5 of them are true predictors. So in this case, the lasso has a better power to identify these true parameters. And in many cases, the reality is more complicated than simple statistical models. So P is equal to 1,000, and actually the most predictors are relevant to response variable. So the D is really large, but still we want to make coefficients more stable. So in such a case, the rich regression works better. And usually we don't know the truth, so we cannot really say which is better. But lasso has the strong advantage that the obtained model is simpler. Rich regression is more natural because we use the squared, the square loss. So we have the quadratic form of beta. So mathematically, it is more natural and the good shape. For example, if you apply the Newton-Raphson method, probably the rich regression, we have the more smoother, predictable, surface. So it's good for optimization. So we cannot say which is better. Yeah. So of course we can think about other cases. For example, the loss function is equal to RSS plus the summation lambda times summation I is equal to 1 to P, the beta P to the maybe the Q's power, and Q is equal to 1, then lasso to rich regression. So in general, that we have Q. Usually the Q outside of 1, 2 does not work, but in general, at least the Q between 1 and 2 have good properties. So this model is possible. And I think another textbook, probably the Elements of Statistical Learning by the same authors. So this book discusses this case, but practically it's not really useful to use this. Suppose the Q is 1.3 is a better gives a better model. That's a possible case, but usually if we think about the Lasso and rich regression, that's enough. If we generalize the Q a little bit, still the performance doesn't get better. So often we just use Lasso or rich regression. So maybe we compare those two, but no more than that. Yeah, so this is our conceptual graphs for how to optimize lambda. So the purple line is the test error, test MSE. So basically we have some place at which the test error is minimized. So lambda gets larger, then the performance gets better. Then after that, it gets worse. So we have to determine this lambda. Now, often, if p is small, actually the lambda is equal to 0 is the best. So that is also the case. But if the problem is they're good for Lasso or rich regression, then usually we have some optimal lambda here. So conceptually, this test MSE can be decomposed into two parts. That is the squared loss and bias. So bias gets smaller if model is more flexible, but the variance gets larger. So remember that the number of parameters in the model. If we have more parameters, it's more flexible, bias is small. So even if the true shape of the curve is complicated, that we can exactly follow this shape. So bias is smaller, but the variance is larger because we estimate many parameters. So it's really affected by few observations. So in real problem that we cannot decompose this test MSE into bias and variance part, so we cannot really observe it. But conceptually, okay, so we have the bias and the variance. So bias is here and the variance is here. So we have some optimal point to minimize the sum of those two. Yeah, mean square error. Yeah, so this is another way to represent it. So lambda gets yeah, so lambda gets larger, then the coefficient that becomes 0. So the R square gets smaller. So that we have slightly different. So basically these two are almost equivalent figure. So R square on training data. So basically we have more flexibility. So more flexible. Or a small lambda. And this direction to the left, basically R square is on training set is small. So that means the model is less flexible. So that means the large lambda. So more restrictive. Model. Yeah, I think that this is a little bit irrelevant. So you can see just the left figure. So you have some optimal point of lambda. Yeah. I think that we have the two cases. Yes. So yes. So okay. So yeah. So basically, okay. So left figure and right figure are corresponding to each other, and we have the dotted line and the straight. Sorry, the solid line. And the solid line is the test MSE for Lasso, and the dotted line is the test MSE by rich regression. And for this data set, the rich regression works almost always better. Yeah, actually, yeah, maybe except for this point, they're almost always better. So this is the data for which the rich regression works better. So that means that we have the true non-zero parameters. For another data set, the situation is different. We still have the optimal lambda, but in terms of the Lasso and rich regression, this is the rich dotted line, and the solid line is Lasso. And Lasso almost always has smaller test error. So that means probably the true model is small, but we have many redundant candidates of predictors. So it really depends on the problem which is better, rich or Lasso. Yeah, so which is better, it really depends on the data. Okay, so now that we have the more concrete example, let's think about the almost simplest linear model. The yj is equal to beta j plus epsilon j. Yes, so this is, okay, so yeah, so this is basically the n parameters for n observations, n parameters for n observations. So this is trivial model, a kind of trivial model. We have n observations and we have n parameters. So yj is equal to beta j plus epsilon j. So if we fit the linear model, we get the yj is equal to beta j hat is equal to yj. So we prepare the n parameters for n observations. So just error becomes 0 and everything can be explained by parameters. So
sorry, Professor.
Yeah.
I didn't understand. What do you mean by parameters and parameters? You mean independent x variables?
Parameters are the numbers we can adjust to fit to the data.
So they are slopes or intercepts?
In this case, the dummy variable, okay, so to be exact, this is the y, okay, so yj is beta 1 times the indicator variable for j is equal to 1 plus beta 2 times indicator variable of j is equal to 2 up to beta n times indicator variable of j is equal to n plus epsilon j. So this is a kind of trivial model, so it sounds strange, but basically this model means the yj is equal to beta j. So we prepare one parameter for each observation. So actually the error is 0. So maybe to answer your question, the beta j is the coefficient for the dummy variable for each specific observation.
I see. Thanks.
Yeah, so this is a kind of a kind of trivial model. So it's motivated by ANOVA model. So sometimes if we have the 3 groups and 6 observations, yeah, 3 groups, 6 observations, then it's possible that for example y12 is equal to beta 1 plus epsilon 1, y11 is equal to beta 1 plus epsilon 1, sorry, epsilon 2 here, epsilon 1, 1 and 1, 2, and y21 is equal to beta 2 plus epsilon 2, 1, and y22 is equal to beta 2 plus epsilon 22, and so on. But here we prepare one parameter for each observation. Okay. But actually the estimate isn't really the bj hat, beta j hat is equal to yj if we use Lasso or rich regression. Okay, so here is the case. So if we use usual least square, just the beta j is equal to beta j hat is equal to yj. Okay, so this is beta j hat. But the rich regression, actually the parameter gets smaller in this way. So it shrinks to 0. So if yj is equal to 1, then beta j hat maybe is equal to 0.8. If yj is 0.5, the beta j sounds 0.4. Beta j hat equals to 0.4. And how about Lasso? So Lasso, actually, it is parallel to the original, the OLS, but the coefficient becomes 0 if yj is small. So between maybe negative 0.4 to 0.4, so the estimated beta j hat is equal to 0. Yeah. So this is consistent with the my explanation that the Lasso makes small coefficients 0, but large coefficient doesn't change much for large coefficients. And rich regression for larger coefficients, it shrinks more. So this is the difference in properties of the rich regression and Lasso regression. And further, we compare the meaning of the rich and Lasso. So when we minimize the residual sum of square, so we minimize the summation of the EI square, residual square, and this is based on basically the likelihood function. So the summation of EI square, this corresponds to the likelihood function, the negative log likelihood function of normal distribution. Then the rich regression minimize RSS plus lambda times the beta j square. So now we want to interpret this term as a random variable. So we interpret epsilon I as just the random variable. So now that we interpret beta j also as a random variable. So that is a kind of the Bayesian interpretation. In Bayesian scheme, everything is random. So parameter is not deterministic, but it's random. And we only estimate the distribution of beta. So under Bayesian scheme, basically the rich regression is equivalent to assume beta j is normally distributed with mean 0 and variance, the inverse proportional to the lambda. Okay. So remember that the normal density is equal to 1 over square root of 2 pi sigma times the exponential of negative x square over 2 sigma square. So if we think about the negative log likelihood of f of x, then okay, so we have some negative log sigma or something, but except for that, this becomes maybe plus. This becomes the plus 1 over 2 sigma square times x square. So that means having this term, this penalization term, means that the beta j has some probabilistic distribution, and which has the mean 0 and also the normal distribution, and the lambda corresponds to 1 over 2 times sigma square. So the inverse of lambda is a kind of variance proportional to the variance of beta j. So in the penalty function, the loss function of rich regression implies that the beta j follows normal distribution with mean 0 and the variance proportional, the inverse proportional to lambda. So that is the Bayesian interpretation of rich regression. And how about Lasso? Lasso has the loss function of RSS plus the lambda times the summation beta j absolute value. And which distribution this corresponds to? And actually, that is the Laplace distribution, or a double exponential distribution. So double exponential distribution is proportional to e to the power negative, so negative the lambda times the x absolute value. So if we take the negative logarithm of this function, I think we have some coefficient here, but basically the log of the negative log of this likelihood is the proportional to the lambda times the absolute value of x. So this corresponds to, this loss function of Lasso corresponds to this negative binomial distribution. Sorry, the double exponential distribution. So that means so without any condition, rich regression assume that the beta j has this distribution. So that means that probably beta j is not really large. Beta j is between -2 and 2 for most cases, but the but the doesn't have very high probability that beta j is exactly equal to 0. So this is the assumption of the rich regression. So with this assumption, with this interpretation, we can see why in rich regression the estimated parameters are small. So originally we have a kind of prior distribution of beta j. So the prior of beta j assume that the beta j is not likely to be very large. So that's why estimated beta j hat isn't really large. And Lasso is here. So this is double exponential distribution. So this is basically the function of beta j absolute value exponential over 1 over maybe negative lambda. Okay. So this Lasso assumes that the beta j is probably very close to 0. And with small probability, it may be large, -3 or 3. So in this sense, the rich regression or Lasso assume that the parameters are small. So around 0. But assumptions are slightly different between these. And since Lasso has higher density for beta j is equal to 0, the more parameter becomes 0. More estimated parameter beta j becomes 0. So this is the characterization of rich and Lasso. So again, it really depends on the case, which is better. Basically, for many parameters, if we have many candidates of parameters, predictors, then Lasso works better. Otherwise, it really depends on the case. Okay, so do you have questions so far? Okay, so next we talk about how to determine lambda. So rich regression, we minimize residual sum of square plus lambda times summation of beta j square, and Lasso RSS plus lambda times summation of absolute value of beta j summation. So j is equal to 1 to p. So how to determine lambda? So without having lambda, we cannot really run this procedure. And the answer is lambda is optimized by cross-validation. So we choose lambda so that the cross-validated error is minimized. Yeah, so if we are evaluating test MSE, basically, we have to do 2 layers of the cross-validation. So we cross-validate the data to estimate something with training set. Then after that, we calculate the test MSE. Then we do cross-validation to evaluate the model performance. So sometimes we have the 2 layers of cross-validation needed to estimate, to evaluate the model, rich regression or lasso. Yeah, so 2 nested CV is possible. So to be concrete, maybe suppose the n is 1000, then how to estimate it? Okay, so think about the 5-fold cross-validation. For checking the test MSE. And possibly maybe the 2-fold cross-validation to choose lambda, then how to do it. So, okay, so that means the 5-fold cross-validation for test MSE. So we have 1000 observations. So we divide this data into 5 pieces. Okay, so D1, D2, D3, D4, D5. Okay, so we use the 5-fold cross-validation for evaluating test MSE. So we make this as test set. And we use the training set. The other 4 as training set. Then we have to evaluate lambda. So we just randomize this D1 to D4 into 2 parts. I don't know how to say this, but suppose this is the set E1 and set E2. Randomize. Then for each lambda, evaluate. I'm gonna estimate model with E1. E1 and test with E2. Then we do the other way around. For each lambda, estimate model with E2, then test with E1. Then decide which beta is, decide what lambda is the best. Then after we determine lambda, we can estimate the model. Then we can test with D5. Then we repeat this 5 times to evaluate 5-fold cross-validation. So it's a little more complicated, right? Yeah. But sometimes we need the 2 layers of cross-validation. Yeah, so statistical procedure sometimes becomes really complicated because of this. So cross-validation is not always good, you can see. Yeah, so do you have any questions?
Yes, I have a question, Professor.
Sure.
For example, if we want to do 5-fold cross-validation, we should repeat this procedure for 5 times. Every time,
correct.
We should separate our first data set into 5 parts, and then 4 of them for training, 1 for test, and these 4 training, randomize them, and then calculating lambda, and then again repeat this 5 times. Yes.
Yes.
Okay, thanks.
Yeah, of course, maybe, sometimes some people want to have a shortcut, maybe they estimate lambda only once. But logically speaking, yeah, you are right. So you have to estimate lambda for each training set in the 5-fold cross-validation process. Yes, you're right. Okay. And this is the cross-validated error. I don't know how exactly all people follow this procedure. Okay. And this is okay. So in this figure 612, basically we ignore the this part, just that we focus on determining lambda. So we cannot evaluate the cross-validated error. Okay, so we only evaluate the optimal lambda. Okay, so suppose data is given, then we do cross-validation, then we estimate the optimal lambda. So optimal lambda is here. So I don't know how many lambda they tried, but if they try different lambdas, then we can estimate the test MS, cross-validated MSE each time. Then we identified that this is the best lambda. And the standardized coefficients, the lambda is larger, then coefficients become smaller. So this is a kind of beta 1 hat, and this is beta 2 hat, and beta 3 hat. And we have dummy variables. So this is maybe beta 4 hat to beta p hat. But the true model only includes the 3 parameters. Then lambda gets larger, then it's not clear, but at least these coefficients get smaller. This becomes actually larger. This looks flat. And I don't know, this one, maybe we have 4 predictors. I don't know. This becomes smaller in absolute values. And these ones, I cannot really see. Yeah. And this is for what? I'm not sure. So this is for rich regression and Lasso. It sounds that this is just one model. So this is probably the rich regression for these two. Yeah, I think that we should have maybe the 2 more graphs. This is probably just for rich regression. Yeah, but we have the optimal lambda. So only the point is we have our optimal lambda. So finally, we choose these parameters. Yeah, so this is how we do rich regression and Lasso. So at first, the step 1, the determine lambda. Then step 2, estimate the model. Yeah. Yes, so this is the procedure for rich regression and Lasso. Yeah. So in old days, people are not really data oriented. So when I studied rich regression for the first time in econometrics, they have some pre-specified lambda. If the data is monthly, lambda should be this, or data is annual, lambda should be this, or something like that. That is not really the data science, but some people use some specific lambda. Maybe, for some specific problems in specific field, they have some experience about the estimation, and the lambda should be around the same value. So maybe some field have consensus on lambda, but in data science, the lambda should be estimated by cross-validation. Okay, so now that we go to the last section, the 6.3, the dimension reduction methods. So we have studied at first subset selection. Subset selection chooses the D parameters out of P. suppose we have 100 candidates of predictors and we choose 5. And the second method is shrinkage method. We studied Rich and Lasso. So we keep P, but we make many coefficients small or sometimes 0. And the dimension reduction methods, that we transform variables. So we have x1 to xp, but suppose that these have very similar information. Then we summarize this into several predictors. So x1, if we have n observations, this is n-dimensional vector, and x to x to x3, x4. So these each of these predictors are n-dimensional vector. But basically, we think about the transformation of variable x1 to xp, and that we create the new predictor z1, z2 up to zm. And if capital M is much smaller than p, then this is a summarized data. For example, p is 100, but the m is 3 or something like that. And we consider the case that the zm is linear combination of x. For example, suppose we have 6 definitions of unemployment rate, but these are very similar. Then we take just average. Then that is the z1, maybe. Or suppose that out of the 6 definition of maybe 6 components of consumer price, then component 1 is food, component 2 is energy, and component 3 is maybe electronics, and x4 is rent or something. Then we just put weight, maybe 20% on food and 10% on energy, and so on. Then we determine this coefficient, then zm is overall the price level. So in that way, the linear combination of xj is the more meaningful than each xj itself. And once we summarize the data, we can regress y on these zm's. Then since capital M is smaller than p, estimation is easier and more stable often. So the problem is how to choose z1 to zm. Okay, so take average. That is simple, but I don't know. We don't know if it's best, right? So probably you don't really question the, for example, university admission system, but what's the meaning of just taking average of the SAT math score and the SAT verbal score and the SAT writing score? So if we take just the simple average, maybe it does not really have the most important information. Right? So we optimize the coefficients. We optimize the definition of ZM. And one method to choose the weight, this the coefficient, the phi of JM, phi sub JM, is the principal component analysis, or called the PCA. So PCA is a technique for reducing the dimension of n minus p data matrix X. So basically X is n minus p, but we summarize this into Z. Z is n minus m, and m is much smaller than p. Yeah. And to define Z, the Y is not involved. So that is one important point of PCA. So this is a kind of unsupervised learning since we ignore Y first. So our idea is we summarize X to Z without considering Y. So then after that, we regress Y on Z. So a kind of the two-step approach. So the summarizing data, summarizing predictors is the first step. Then second step, that we relate Y with Z. Yeah, and in PCA, each component, the Z1 to Zm, is defined as the projected the position of each row vector of X onto the straight line. Maybe it's good to show the example. So this is the data with two predictors. We have X1 is population, X2, X is the advertising spending probably the population of the market and the advertisement spending of some company on the market. Then you can see that the basically, the larger population, then larger advertisement spending. So we have some relationship, and if we choose this green line and we project each observation onto this line, then that becomes basically the principal component. And the principal component choose the first component, so that the variance of this component is the largest among all the direction. So you can see that if these points are projected onto this green line, the variability is large. So center may be here, and the variability is large from here to here. So variability is large. On the other hand, if we project all observation onto the blue line, then variability of these points are smallest among all directions. So we use this as the first principal component. So basically the signed distance. So distance from here. So this distance, maybe the other way, we have negative distance. So this distance from here, the center to here, each point. So this is the defined as the first principal component. So signed distance is defined as the first principal component. So in case of the multiple predictors x1 to xp, the direction with the largest projected variance is called the first principal component, and the second principal component is orthogonal to the first component and has the largest variance given that condition. So then we define the second principal component, then the third and the fourth, and so on. If we have p predictors, we can calculate up to p principal component. And usually the first few have the most important information, and the others have a very small amount of information, almost noise. Yeah, so straight line for the first component is chosen so that the variance of the projected position is maximized. And the straight line for the case component zk is chosen so that the variance of the projected position is maximized, subject to xk, zk is orthogonal to the z1 to zk minus 1. So this is two-dimensional case. So this, and a two-dimensional case, yes, yep. Yeah, so this is another figure to explain that. So we consider the projected distance for this observation. Projected distance is here to here. This observation, projected distance is here to here. So if we consider the direction, then we can have the first principal component. And the first principal component, Z1, usually has the large positive or negative correlation with each of the predictors, X1 and X2. So Z1 is highly correlated with X1, and Z1 is also highly correlated with X2. So sometimes we have the negative relationship, but the usually correlation coefficient is large in terms of absolute value. And on the other hand, the second principal component, we only have the two predictors. So second principal component is the least irrelevant information, or least the representative information of X1 and X2. So we can see that the X1 correlation between X1 and the Z2 is very small in absolute value. And the X2 and the Z2 also almost no relationship. So the Z1 has most important information. Z2 has really the small amount of information. So in this case, probably we can ignore the Z2 and we can only use the Z1 to explain the response variable Y. Do you have questions so far? Have you ever used principal component somewhere else? No. So principal component analysis is used, especially when we have many predictors, such as image data. Image data is generally large, such as 100 by 100 pixels. So this is often used. And principal components may and may not be interpreted in the context of data. So for example, consider the test scores for 1,000 students. There are 5 scores: the English test score, and math test score, science, and social studies, and French. So each student have the 5 data points. So English, math, science, social studies, and French. And suppose that the first component is this. So 0.45 times E plus 0.45 times M plus, okay, so all coefficients are similar. Here actually the same, 0.45. Then first component means the overall performance of the student. So sometimes we have slightly different values, but this is just the all positive value. So just the overall performance. If we have maybe math test score, the component, the coefficient is 0.9, maybe the math test score is more important to represent the overall quality of students. And how about second component? Sometimes we can interpret it, sometimes we cannot. Suppose we get this. Second component is negative 0.5 times E plus 0.5 times M, 0.5 times S, 0 times SS, negative 0.5 times F. Then, okay, you can see that the 0.5 and 0.5 for math and science, and negative 0.5 for English and French. So we can guess that some students are good at math and science, but not good at English and French. And the other way around, some students are good at English and French, but those students are typically not good at math and science. If such tendency exists, then second component may be tendency towards scientific areas. But if coefficients are different, then sometimes we cannot really give the interpretation. So it's really subjective, and it's not logical or mathematical. But often we can interpret the first 1 or 2 principal component.
How can we determine these coefficients? For example,
coefficient is determined by the algorithm by this. So we maximize the variance of Z1. We will discuss the mathematical argument later, but basically it's automatically determined by this method. So Z1 should have largest variance. Z2 should be orthogonal to Z1 and has largest variance, and so on.
Thank you.
Sure. Yeah. So these are automatically determined. So sometimes we can interpret it, sometimes we cannot. Okay, so now mathematical formulation. So we would like to maximize the projected distance to determine Z1. So how to determine that direction U? I mean the coefficient U. Then projectiles, Then if we use inner product, we can express this in an easier way. So let x1 tilde to xn tilde be row vectors of x. So x is n by p. So last time that we expressed the first variable to p's variable. For example, if first variable is English score, then x1 is the 1,000 students the English score. But now that we think about the each student's score, so x1 tilde is the first student score. This is 5-dimensional vector, so p-dimensional vector. Then x2 tilde up to xn tilde. So 5 test scores for each student. So one specific student, that is x1 tilde. Second student, x2 tilde, and so on. Then we want to maximize the variance of x tilde in the product U. So if x1 tilde is equal to x11 to x1p, then the U is equal to U1 to UP, then x1 tilde in a product U is the x11 U1 plus up to x1p UP. So suppose that the U is unit vector. So U is vector which satisfies the length is equal to 1. Then basically we want to maximize the variance of x tilde times U. Then the U is the direction.
Sorry, Professor.
Yeah.
I didn't understand why we want to maximize the variances. What is the theory or logic behind that?
Yeah. So that is to deduct the most information from the variables. So yeah, here. So suppose that we have 2 variables, x1 and x2, population and advertisement spending. And but we would like to use only one variable, z1, which is the linear combination of x1 and x2 to represent most of the information in x1 and x2. Then you can see that if we see these observations, basically some observations are on the upper right side, and some observations are on the lower left side. So the characteristics is that whether these two the characteristic is that each data point is generally larger value on both x1 and x2, or small value for both x1 and x2. Right. So the variation with this direction is large, but the variation of the data for this direction is small. So this is not important feature, and this is important feature. So that is the concept of the principal component analysis. So if we have some data, and if we have the larger variability in some direction, that is the most important information. So
we want to cover the most variances, right?
Yes.
Okay, thanks.
Yeah, so of course it depends on the context whether first principal component includes important information, but in most cases that's true. And to explain, the most variability is the most important factor. So think about the English test score and math test score example. Suppose some students are good for both exams and some students are bad for both exams. Some students in the middle. So if you are admission officer, what's the criterion to choose students? Then it's possible to make M-E as admission criterion, but probably most people don't think this is appropriate, and probably the most people think that this direction is most appropriate. So that's the point. Okay, so then we want to maximize this variance. So that if we determine u such that this variability is maximized, then that is the u times x tilde is the first principal component. So remember that the u times x tilde that represents the projected distances. So because if u is this direction, and we have vector x tilde, then projected distance from here to here. So this is x tilde times u, x tilde inner product u. So if the x tilde is the other side, I mean the angle between u and x tilde is more than 90 degrees, then x tilde u inner product is negative. So x tilde dot u is the signed distance, signed projected distance. So we want to maximize this signed projective distance, so that we want to maximize this variance of x tilde dot u. So we have to choose u such that this is maximized. Yeah, and usually we assume that the x has mean 0. Each column of x has mean 0. So yeah, so this is the equivalent to maximize this quantity. Yeah. So this each row of xw, so this is the x1 tilde up to xn tilde. Sorry, maybe u becomes w, but the w, right? So the first component is x1 tilde times w. So the inner product of x1 tilde and w. So we want to maximize this quantity. So that is the we have to take square of it and take summation of it. I is equal to 1 to n. So that is equal to this. And how to achieve this? And actually, when w is the eigenvector for the largest eigenvalue of x prime x, then actually this quantity is maximized. Yeah, you can. So I don't prove it, but if the size of x tilde x prime x w is the maximized, then basically we multiply the w prime, then it will be maximized, right? So largest eigenvector corresponds to largest eigenvalue. The eigenvector with the largest eigenvalue that corresponds to the direction of first component, first principal component. Yeah. Yes. So that is the principal component analysis. And usually the column vectors of x is standardized to have mean 0 and variance 1. So that means if x is, for example, 1, 0, negative 1, and maybe I don't know, 110 and 10 and negative 90, then it should be standardized to have the mean 0 and the variance 1. So suppose this is x1 and this is x2, then it should be standardized. X1 maybe this is standardized already. So then the x2, we have to standardize it. So this is shifted by 10 and multiplied by 100. So that this becomes 1, 0. Actually, this becomes same, so it's not good. So maybe I would say negative 90 and 110. Then we get -1, 0, 1. So in this way, that is x2 should be standardized. So x2 something, x2 0 maybe. So we have to standardize it. Otherwise, the principal component analysis just takes the variance with takes the direction of the large. Sorry. Suppose we have x1 and x2, and x2 has much larger variance, right? So if we calculate principal component with this matrix, then first principal component z1 is almost equal to x2, because to maximize variance, just we choose vector with larger variance. So that does not make much sense, because that just depends on the scale of x2. If we change the scale of x2, the unit of x2, the result changes. So usually we standardize this x. Then after that, we determine what is the z1. So in this case, actually the x1 and x2 are just the opposite. So x1 is negative x2 or something. So probably the z1 is x1 plus x2, x1 minus x2 or something like that. Yeah. Maybe two, yeah. So usually the coefficient is a unit vector, so maybe it becomes maybe square root of 1 over square root of 2x1 minus 1 over square root of 2x2 or something like that. Yeah, so principal component will be similar to column vector with large variance. If standardization is not done, just principal component becomes the vector with the largest variance. So it's not really useful. So it becomes scale invariant. So usually we standardize it first, then we calculate the principal component from this vector. Yeah, in computer science, the presentation, without saying anything, every variable is standardized. Maybe in some other field, such as economics, the social science, maybe not. Yeah. Do you have questions? Principal component regression. So this is not really complicated. So maybe we can discuss it. So just the idea is that we use the z1 to zm instead of x1 to xp. So suppose the p is much larger than m, then it's much useful to use the several principal components. So if suppose 99% of the variability in x1 to xp are explained by z1 to z3, then we can just regress y on z1 to z3. Then we can deduct most information. Yeah, so information is sufficiently summarized, so the performance is better. So you can imagine that, for example, the AIC. AIC is negative log likelihood plus 2 times number of parameters. If P is large, penalty is large. That is not good. But if you use principal component regression, this becomes much smaller. So you can see it's much more preferable. And we know that this is basically, this maximizes the prediction performance. So if you summarize the data beforehand, then it works much better. Also, Z1 to Zm are orthogonal. So that means that we have no problem of multi-collinearity. Yeah, so if if the P is very large, then we can combine the method such as Lasso or stepwise selection with principal component. For example, the P is 2000. And we summarize it and the M becomes 20. Then we do stepwise regression. then finally that we choose maybe only 3 variables or something like that. So usually it does not make much sense because the first principal component is most important, second principal component is second most important. So usually the first few components are important. So it's really not. So it's rare that the model chooses Z1 and Z3 and Z6. That's rare. But at least to determine M, maybe we can choose some methods such as stepwise procedure. Yeah, so especially P is larger than N, we have the estimation problem, identification problem. But if we use principal component beforehand, we can choose M such that M is smaller than N. So we can avoid this problem. So this is the principal component analysis and the usual linear regression. And this is number of components. Okay, so you can see the purple line is the optimal one. So probably this is optimal point. Possibly here. So this is about 15. This may be 23 or something. But if we don't use principal components, then the best point is around here, 32 or something. So we can choose much smaller than number of coefficients. And still, you can see the performance is almost the same, maybe even better for this one. So principal component analysis works better. Yep. So next one is partial least square, but this is a different model and a little more complicated. So idea is that we use information of Y to summarize information of X. It's a kind of ad hoc method, but at least we have to maximize we have to utilize the all information at maximum. So to summarize the X1 to XP, we use the information of X and also Y. So that is the idea of partial least square. But this is a more complicated model, so that we explain it in the next time.